This is page 2 of the chi-squared packet. Number 2, a survey was conducted to find out which type of bread males and females prefer. This sounds like the lamest IA I've ever heard. 80 people were interviewed outside a baker's shop, and the results are shown below. Okay, so across the top we have the different kinds of bread, and across the side we have male and female, and across the bottom and the right edges we have the totals. That is not part of the contingency table or matrix. It is just the totals. Okay, so we don't put that in the calculator later. Using the chi-squared test at the 5% significance level, so that means 95% sure, certain, determine whether the favorite type of bread is independent of gender. Okay, so actually they've almost already given us the null hypothesis. Let's state the null hypothesis. The null hypothesis is that blank and blank are independent, and in this case it is favorite type of bread and gender. So I'm going to put gender and preferred bread are independent. That is the null hypothesis. And the alternative hypothesis is the opposite of that, that gender and bread, preferred bread, are not independent. Easy, right? Okay. Show that the expected frequency for female and white bread is approximately 17.9. This is the same thing as the previous page, right? So we look at female and white bread, and then we look at the subtotals that correspond to those, and we look at the grand total, and we just multiply. We make two fractions out of that, 41 over 80 and 31 over 80, and we just multiply those two together because that's going to give us a big fraction that we're going to multiply times the grand total of 80. Okay? So that would give us the expected frequency. If we multiply that out, we're going to get 17.9. Okay? And the way you do that on the calculator, just to review, I'm just going to do it once on this page, okay? We could put it like this, 41, and definitely use plenty of parentheses, right? 31 divided by 80 times 80. Well, we don't need a parentheses for the last one, right? Because 80 is just a number. And that gives us 15.9, which is not at all 17.9. I think this is some kind of misprint. I checked it and double checked it, and it is definitely 15.9 instead of 17.9. So let me just write here that it is 15.9. Okay. And then it says to write down the number of degrees of freedom. There's two ways to do that. One is that we say, okay, the number of rows is 2, the number of columns is 4. I can do 2 minus 1 times 4 minus 1, and that gives me 1 times 3, so the degrees of freedom is 3. Or you could look at the white matrix right there, and you say, oh, well, of this white matrix, the numbers that we can choose freely are these 3, and after that the others are all calculated, so the degrees of freedom is 3. Write down the chi-square statistic and the p-value for this data. I've already put this matrix in the calculator, so if we go into the second matrix, edit A, we can see the A matrix, which is this one, 14, 17, 10, 6, 7, 6, and 8, 12. And then we just run the chi-squared test, which is stat test. We go to the second page. You either go up or down to go to the second page, and you click on option C, which is chi-squared. And we leave B as the expected matrix because that's going to be filled in when we run this. The chi-squared value is 2.19, and the p-value is 0.548. And the critical value is 7.815, so we compare 2.19, which is the chi-squared value, with the critical value, and it's less than the critical value. And so remember, if the chi-squared value is small, the data is not extreme, it's just regular independent data, so we can't accept the null hypothesis. So the chi-squared value is less than the critical value, so we accept the null hypothesis, or you could say we do not reject the null hypothesis. Okay, let's go down to number 3, which is below. 300 people of different ages were interviewed and asked which genre of film they mostly watched, thriller, comedy, or horror. The results are shown below. The people are divided into 3 different age groups, and there are 3 different types of movies. So this is obviously a 3 by 3. We're going to use that later when we figure out degrees of freedom. Using the chi-squared test at a 10% significance level, determine whether the genre of film watched is independent of age. State the null hypothesis. So null hypothesis would be genre, movie genre, and age is independent. And what is the alternative hypothesis? Movie genre and age are not independent. Okay, pretty easy, except maybe easily confused or mixed up also. Show that the expected frequency for preferring horror films between ages of 20 to 50 years old, so it would be that subtotal there, is 33.4. So we're looking at horror, which would be 77 out of 300, and we're looking at 20 to 50 years, which is 130 out of 300, and we're going to multiply those two together. So we're going to have 130 divided by 300 times 77 divided by 300 times 300, and that should give us 33.4 if everything works out, but we just saw that the other one didn't work out, so I'm going to go to ND, N over D, because I can like type everything in without parentheses. It's kind of more quick and convenient. So it's 130 times 77 times 300 divided by 300 divided by 300 times 300. And I do want to turn this into a decimal. So I'm going to do math, decimal, enter. And my answer is 33.4, and that was what I was supposed to get, so great. Write down the number of degrees of freedom. So the degrees of freedom, if for a 3 by 3 matrix, would be 3 minus 1 times 3 minus 1, so that would be equal to 2 times 2, which is 4. So the degrees of freedom would be 4. Write down the chi-squared test statistic and the p-value for this data. So the chi-squared test statistics we get by doing the stat-calc linreg, not the stat-calc, stat-test chi-squared option. And first thing we're going to have to do is we're going to have to enter this data into the A matrix. First, we're going to say that it's a 3 by 3, and the rest of the time we're just going to input the data, and I'll do that offline. Hold on a second. Okay, I just put everything into matrix A, so now we can go to stat test option C, which is chi-square test. We put AB for observed expected because we filled in everything into A. And our new chi-squared value is quite large. It's 45.2. And our p-value is quite small. It is 3.59 times 10 to the negative 9th, which is really small. 10 to the negative 9th is 8 zeros, 0.0000008 zeros, 359. So that's small. The degrees of freedom is given by the calculator, but that's pretty easy to calculate when you look at the matrix. And if we're going to comment on a result, we are going to say that chi-squared is less than, or wait, where's the critical value? The critical value is, I think they did not give us the critical value. So if they don't give you the critical value, then you're forced to use the p-value, okay? And so the p-value, this very small number here, we're going to test to see if the p-value is smaller or larger than the significance level. The significance level is 0.10, so obviously the p-value is much smaller than the significance level. And if the p-value is smaller than the significance level, then we reject the null hypothesis. Okay, if the chi-squared value is smaller than the critical value, then we would accept the null hypothesis. But p-value works exactly the opposite. So when the p-value is smaller than the significance level 0.10, then we reject the null hypothesis. Okay, and it makes sense to reject the null hypothesis because look how big the chi-squared value is. It's quite large. So even though I don't see here whether they gave us a critical value, yeah, I don't think they gave us a critical value. So since they didn't give us a critical value, we can't assume that 45.2 is bigger than the critical value, but we can use the p-value. Okay? All right, let's go to number 4. 3 different flavors of dog food were tested on different breeds of dogs to see whether there was any connection between favorite flavor and breed. The results are shown in the table below. So I'm going to color in the bottom row and the column on the right. And then I'm going to look at the remaining white matrix here. Perform a chi-squared test at the 5% significance level to test whether favorite flavor is independent of breed of dog. State the null hypothesis and the alternative hypothesis. Okay, null hypothesis, pretty easy. Null hypothesis is just blah 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 and blah 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 are independent. So in this case, the 2 factors are dog food flavor and breed of dog. So breed and dog food flavor, breed and flavor are independent. That is the null hypothesis. And the alternative hypothesis is just the opposite of that. Breed and flavor are not independent. Okay? All right. Let's move on. That was A. Write down the table of expected frequencies. Okay, so the table of expected frequencies, they don't ask us to find the expected frequencies of Labrador and chicken or whatever. They're asking us to figure out the whole thing, but they're not asking us to demonstrate it. So then we can take advantage of the capability of the calculator, and we can use the calculator to figure it out. And so the first thing I'm going to do is I'm going to change the matrix to a 4 by 3 matrix because the white section is 4 by 3. So I'm going to edit matrix A, and I'm going to change it to 4 by 3. And when I change it by 4 by 3, now it makes an extra row there. And now I'm going to just fill in all the white values here, and I'll do that offline. Hold on a second. Input everything into matrix A. I ran stat test chi-squared. Once I do that, I can get out of this screen and check the matrix B, because matrix B now has everything filled in. So if I look at matrix B now, it has all the expected frequencies filled in, and they said they wanted to know all these expected frequencies, so I'm going to put the expected frequencies into this little table here. So 11.77, 9.33. Just put in 3 significant figures because that's what they usually want. 9.5. On your IA, you would probably put more than 3 significant figures. 6, 8.75, 11.7, 7.92, 4.75, 6.33. Okay. So this is the expected frequency matrix. So I'm just going to write down the dog breeds or whatever. So it'll be beef, chicken, lamb, boxer, Labrador, poodle, and collie. Okay. Now there is a slight problem here. The slight problem is that normally when you're doing chi-square testing, the expected frequencies should all be above 5. And we have one value here, which is 4.75, slightly below 5. When you have a value slightly below 5, then you need to use like something called Yates continuity theorem, and it's kind of a lot of trouble. The better thing to do is try to adjust your table so that you don't have anything less than 5 by grouping together some things. So let's see if we can do a grouping that would help here. So let's look. Combine the results for collie and poodle so that all expected values are greater than 5. So if we combine poodle and collie, then the expected values would be more than 5, right? So how do we do this? What we're going to do is we're going to take this table and we're going to combine the poodle and collie numbers in a new data set. Okay, so we're going to do that in this table here. So we got beef, chicken, lamb, and we have boxer, Labrador, and poodle plus collie combined in the last row here. So let's see what the numbers are. 14, 6, 8. I'm making a new contingency matrix, right? 14, 6, 8, 17, 11, 10. This is something that you might do on your IA. You would group together categories in order to make sure that all your expected values are greater than 5. And we'd have 19, 13, 19, 13, and 22. All right. So we have a 3 by 3 matrix now, and probably with this 3 by 3 matrix, the poodle and collie chicken box would probably have a number that is closer to, or that is more than 5. So no problem. So let's. So now what we're going to do is we're going to do the chi-squared test for these numbers. And so the way we're going to do that, we're going to go back to second matrix and go to matrix A. And now instead of a 4 by 3, now we want a 3 by 3, right? So I'm going to get rid of the last row. And then instead of 13, 8, 14, I'm going to put our new last row, which is poodle plus collie. So it'll be 19, 13, and 22. And then I'm going to do stat, test, option C, chi-squared test. Okay, and then our chi-squared value for this new smaller table is 3.14. And the p-value is 0.535. The critical value is 9.488. So if we take our chi-squared value and compare it to 9.488, we can see that the chi-squared value is less than the critical value. So we reject the null hypothesis. Or I'm sorry, we accept the null hypothesis, because when the chi-squared value is small, the data is independent. So we accept the null hypothesis. Okay? I think that's it. And if we want to, just for curiosity, we can check the new expected frequencies in B. And if we look at it now the third row has all numbers that are greater than 5. So we don't need to use the Yates continuity theorem anymore, and we have a good start for an IA. Okay? So that's it for this page.